Bismillahirrahmanirrahim. Welcome back with lecture 8, discrete structures. First, we discussed the previous lecture summary. In previous lecture, we discussed about the properties of relations, reflexive, symmetric and transitive property relations, properties of Lassam relations, and also we discussed properties of congruous modulo 3 and transitive layer of relations, combining relations and the related induced by a partition. Now we will discuss about the functions. Functions. Basically, we will discuss about the one-to-one function, on-to function, bijective functions, which is one-to-one correspondence, and inverse of the functions in the half lecture. And next we will discuss about the inverse function for infinite sets also. And first we discuss about the sum and difference of two functions. Let f is a function from R to R, and G is another function from R to R. These are two functions defined. If we define a new function f plus g from R to R for all x belongs to R, then f plus g of x is equal to f of x plus g of x. You can see that f minus gx is equal to f of x minus g of x. So I here wrote plus and minus both. So it's sum or difference of two functions. So you can add two functions, you can subtract two functions. So this is the way to sum and differ of two functions. Let f and g must have same domains and codomains. If f plus g of x is equal to f of x plus g of x, f of x is 2x plus 3 and g of x is x minus 1, then f plus g of x is equal to 2x plus 3 and plus this x minus 1. So this will become 3x plus 2. So this is the sum of these two functions f and g. Similarly, we can subtract these two functions f minus g. So if we take f minus g of x, so it's 2x plus 3 minus x plus 1. So this will become 2x plus 2x plus 4. So now we discuss about the equality of functions. If a function f from x to y and g from x to y are two functions, then f is equal to g if and only if f of x is equal to g of x for all x belongs to x. We can say that the functions, if they are same, then their domains and ranges are also same. Here we take an example where J3 is equal to 0, 1, 2 and define functions f and g from J3 to J3 as follows. For all x in J3, f of x is equal to this mod 3 and g of x is equal to this mod 3, x plus 2 square, and here is x square plus x plus 1 mod 3. Do you know about the mod 3? We have already discussed in the previous lecture. Now question is that does f is equal to g? So we can check here j from f from j3 to j3 and also g from j3 to j3. We take f of 0. This is the j3 0, 1, 2. F of 0. If we put here f of 0, this will become, what do you think about the answer? It is 1. And if we put here 0, then this will become 4 mod 3. The answer will be 1. So f of 0 and g of 0 have the same answer. F of 0 also 1 and g of 0 also 1. I have I put the answers in the next slide also, and you can check if we put here x is equal to 1, f of 1, and here we put 1, so this will become 9, 3 raised to the power 2, 9, so mod 3 it's 0, and here this will become also 3 mod 3, this will become 0. So you can check in the next example in the next slide. Here I put in the table x square plus 1 plus x is f of x is this mod 3, and here's g of x. You can see that it is f, and this is g. So g of x is equal to x plus 2 square mod 3. F of x is equal to this 1 mod 3. This will become 1, and x plus 2 square is 4. So 4 mod 3 is equal to 1. And similarly for x is equal to 1, this will become 3, and 3 mod 3 is 0, which I have discussed in the previous slide, and this will become 9. So 9 mod 3 is equal to 0. And if we put x is equal to 2, then this gives 7. 7 mod 3 it's also equal to 1, and this will become 16. 16 mod 3 will answer 1. So we can check that the answers of f and g are same. So f of x is equal to g of x. I have already solved this example in this slide. Now we discuss about the one-to-one functions. What is one-to-one? Actually, injective function, you can say that. One-to-one means one output, one input, one output, and the same output is not for any other input. If we discuss the definition, let f be a function from a set x to a set y. Then f is one-to-one or injective if and only for all elements x1 and x2 in x. If f of x1 is equal to f of x2, then x1 is equal to x2. Or equivalently, you can see that if x1 is not equal to x2, then f of x1 is not equal to f of x2. P implies Q, negation P, Q implies negation Q. Logically, you can say that. Symbolically, we discuss about this as f from x to y is one-to-one if and only for all x1, x2 belongs to x, if f of x1 is equal to f of x2, then x1 is equal to x2. One-to-one function, here is the example which shows that this is set x 1, 2, 3, 4 and 5. Here is the set y 5, 6, 7, 8, 9. So one-to-one means this one, this input gives the output 5, and this input gives output 6. So this is x. If this x1, this f of x1. So for f of x1 is equal to, if this is x1, we say that x1 is equal to 2 and x2 is equal to 3. So f of x1 is equal to 6. F of x2, if we say this is f of x2, then the answer will be the same, 6. So For one input, you can see that one output. Here, if we discuss here another entry 10, for example, we put here 10, 5, 6, 7, 8, 9. So the domain of this function is this whole set X, and codomain is the whole set Y, and the range of this function is only 5, 6, 7, 8, and 9, and 10 is not in a range. Remember that codomain is a different and range is a different set. Range is the only the answers which we get. You can see that the only outputs which you which you get, and there is a difference between codomain and range. Usually students say that the first set X is domain and this is range. It's strong. This set is codomain and the range is the subset of codomain. Whether it's proper subset, whether it is improper subset. One-to-one functions, we identify here one-to-one functions defined on sets. The domain of F is this A, B, C, D, and the codomain of F is this set, whole set Y, and the range is U, W, X, Y. Domain of G here is A, B, C, D, and the codomain of G is U, V, W, X, and Y. F of x1 is equal to f of x2 for all x1 is equal to x2. So this function is 1 to 1, not on to even u is not pre-image of anyone, but it's 1 to 1 function. If we discuss this function, here we see that A gives the output W and C also gives the output W. So f of x1 which is equal to f of x2, A and C are different, but the function value of A and C is same. So it's not 1 to 1 function. It's a good example. You can understand. One-to-one functions on infinite sets. If we discuss about this, we suppose f is a function defined on an infinite set X. So by definition, f is 1 to 1 if and only if the following universal statement is true. For all x1, x2 belongs to X, if f of x1 is equal to f of x2, then x1 is equal to x2. Thus, to prove f is 1 to 1, you will generally use the method of direct proof. We suppose x1 and x2 are the elements of X such that f of x1 is equal to f of x2, and we show that x1 is equal to x2. To show that f is not 1 to 1, you will ordinarily find elements x1 and x2 in X, so that f of x1 is equal to f of x2, but x1 is not equal to x2, as was shown in the previous slide. We define a function f from R to R and g from z to z, set of integers, by the rules that f of x is equal to 4x minus 1 for all x belongs to R, and g of n is equal to n square for all n belongs to z. Is the function f is 1 to 1? We prove it or give a counterexample. If g is 1 to 1, prove it or give a counterexample also here. Well, suppose x1 and x2 are real numbers such that f of x1 is equal to f of x2. We must show that x1 is equal to x2 if this is 1, 1. By definition of the function f, for x1 minus 1 is equal to 4x2 minus 1, because x1 is equal to x2. F of x1 is equal to f of x2, it implies x1 is equal to x2. If x1 is not equal to x2, it implies 4x1 is not equal to 4x2. If we add 1 on both sides, it will give 4x1 is equal to 4x2. If we divide the 4 on both sides, this will becomes x1 is equal to x2, which is what was to shown here. Counter example: if the function g from z to z is defined by the rule g of n is equal to n square for all n belongs to z, then g is not 1 to 1. Let n is equal to 2 and n is equal to minus 2. Then by definition of g of n1 is equal to g of 2. G of n1 is equal to g of 2, because n1 is here the value 2. So g of 2 is equal to 4, and also g of n2, which is minus 2, it also gives 4. And so the function values of both n1 and n2 are same, but they are different. n1 is not equal to n2. So g is not 1 to 1. For 1 to 1, these should be equal for the function values. Onto functions on sets, it's also very important. Let f be a function from a set x to a set y. F is onto, or it may be said surjective, if and only if given any element y in x, it is possible to find an element x in x with the property that y is equal to f of x, the function value of symbolically f from x to y is onto if and only for all y belongs to y there exists x belongs to x such that f of x is equal to y. Mean to say, in every element in codomain is the output of any element from the domain. F from x to y is not onto if and only there exists y in y such that for all x belongs to x, f of x is not equal to y. If range is equal to codomain, then f is onto. Simply, it's very simple definition here. I wrote for you people. If the codomain becomes the range, it means there is no element in the f of x, the image, which is not assigned with the domain elements. So it means that uh, all the elements of the second set be assigned, so that function is onto. Here we shown in as a diagram, x is the domain of f, x all elements of x, here y is codomain, all the element of y, whether it's not 1 to 1 but it's onto. If here we leave an element like this which don't have any pre-image, so this is not onto function. At least one element in y does not the value of any element from x, so this is not onto function. So it's simple. If the codomain becomes range, here codomain is have 4 elements, we have 5 elements, but in range only 4 elements, so it's not onto. Here is the domain of f. We shown that the codomain of f y. Here this function is not onto because this element y is not to be related to any element in X and does not have any pre-image. And if we discuss about this, for all elements in Y, they are pre-image of any element in X. So this is onto function and this is not onto function. If we discuss about onto functions on infinite series, we know suppose f is a function from a set x to a set y, and suppose y is infinite. By definition, f is onto if and only if the following universal statement is true. For all y belongs to y, there exists x belongs to x, such that f of x is equal to y. Thus, to prove f is onto, you will ordinarily use a method of generalization for generalizing from the generic particular. Suppose that y is an element of y and show that there is an element of x with f of x is equal to y. To prove f is not onto, you will usually find an element of y such that y is not equal to f of x for any x in x. So it is a general example of our onto functions on infinite set f from R to R, and h is the function from z to z. By the rule, f of x is equal to 4x minus 1 and h of n is equal to 4n minus 1 for all n belongs to z, and here x all belongs to R. Is f is onto? Is h is onto? We check here, and if not, we give a counter example. M is equal to h of n, which is 4n minus 1. M is equal to 4n minus 1, so n is equal to m plus 1 by 4. To prove that f is onto, you must prove that for all y belongs to y, there exists x belongs to x, such that f of x is equal to y. So f of x is equal to f of y plus 1 by 4. F from R to R. So does f really send to x to y? So here x belongs to R and y belongs to R, f of x is equal to y. Similarly, in this, f of x is equal to this and f of y plus 1 by 4. We put the value x. If a function f from R to R is the function defined by the rule f of x is equal to 4x minus 1 for all real numbers x, then f is onto. We prove here y is equal to f of x, which is 4x minus 1, and y is equal to 4x minus 1. Let y belongs to R. We must show that there exists a x in R such that f of x is equal to y. Let x is equal to y plus 1 by 4. F of x is equal to f of y plus 1 by 4. So it will become, in if we put here x instead of y plus 1 by 4 minus 1 by definition of the function, and by the basic algebra we cancel out these 4s, so 5 plus 1 minus 1, which is equal to y. So this was to show, this was what was we have to show. If the function h from z to z is defined by the rule h of n is equal to 4n minus 1 for all integers, and then h is not onto. M is equal to h of n if we take, suppose for all m belongs to z, n is equal to m plus 1 by 4. There exists n belongs to z such that h of n is equal to m. So m is equal to n is equal to m plus 1 by 4. If m is equal to 2, m is equal to 0, m is 0, n is equal to 2 plus 1 by 4, 3 by 4, which doesn't belong to z. If m is equal to 0, then it's 1 by n is equal to 1 by 4, which does not belongs to z. So that's not onto function. If the function h from 0 to z is defined by the rule h of n is equal to 4n minus 1 for all integers n, then h is not onto. We give a counter example for this. The codomain of h is z and 0 belongs to z, but h of n is not equal to 0. For any integer n, or if h of n is equal to 0, then 4n minus 1 equal to 0 by the definition of h, which implies that 4n is equal to 1. So you can add 1 on both sides. So n is equal to 1 by 4, which doesn't belong to the set of integers. But 1 by 4 is not integer, hence there is no integer n for which f is, so f is not 1, 2. So f is not, so we can say that on one-to-one correspondence or bijection. Bijective function, you can call this function bijective or bijunction. If the simple, if we discuss about this function, we can simply say that if the function is one-to-one as well as onto, then it's bijective. Bijective actually means combining two things, basically combining two things. One is the onto, and the second is one-to-one. This we give here the example of bijective. It is 1 to 1 also, and no element left in the codomain. So this function, this diagram is shown the function or bijective function. We can show by this example: a with 5, b belongs to 2, c belongs to c. These are the domain and these are the codomain. These are the range. And if codomain uh, becomes the range and the number of elements in domain equal to the number of elements in range, you can see that that function is bijective. Here I wrote that one-to-one and onto, then it's equal to bijective. You can see that if we add these two functions, one to one and onto, then that function will become bijective function. It's very simple, and it's important function. And the one is called injective function, onto function is called surjective function, and this, if we add these two functions, then this will become bijective function. Now we discuss about the inverse functions. Here's the theorem. Suppose f from x to y is a one-to-one correspondence, that is, suppose f is one-to-one and onto. Then there is a function f inverse from y to x that is defined as follows. In the given an element y in y, f inverse y is equal to that unique element x in x such that f of x is equal to y. In other words, you can see that f inverse of y is equal to f if and only if y is equal to f of x. The f inverse is called the f inverse function. We denote it by f inverse. X is equal to domain of this and y is equal to the codomain of this. If function goes from x to y, then it's simple function, and if it goes from y to x, then it's f inverse. Then in inverse functions, the codomain becomes the domain and the domain becomes a codomain. Actually, if we interchange the inputs into outputs and outputs into inputs, then it will become inverse function. Here the function f from R to R defined by the formula f of x is equal to 4x minus 1 for all x, for all real numbers x, for any particular but arbitrary chosen y in R. By definition of F inverse of y, that is unique real number x such that f of x is equal to y. But f of x is equal to y? It means f of x is equal to 4x minus 1. We put here this value. So by definition of this function, so from here we calculate the value of x by in changing the both sides. X is equal to y plus 1 by 4, basic algebra. So x is basically f of inverse. You can say here it as f of inverse y is equal to y plus 1 by 4. If x and y are the sets, f from x to y is 1 to 1 and on to, then f inverse from y to x is also 1 to 1 and on. Simply you can say that if a simple function is bijective, then the inverse of that function is also bijective. That's very important. F inverse is 1 to 1. Suppose y1 and y2 are the elements of y, such that f inverse of y1 is equal to f inverse of y2. We must show that y1 is equal to y2. Let f in x is equal to f inverse of y1, which is equal to f inverse of y2. Then x belongs to x, and by definition of f inverse, f of x is equal to y1, and since x is equal to f inverse of y1 and f of x is equal to y2, and since x is equal to f inverse y2, so consequently y1 is equal to y2. Since each is equal to f of x, that is what was to shown, f inverse is onto. Here we show that it's onto. Suppose x belongs to x. We must show that there exists an element in y such that f inverse of y is equal to x. So let f y is equal to f of x, then y belongs to y by the definition of the function. So it's equal to x. So this is what was to be shown. Here we present the half lecture summary which I have discussed in the previous 28 slides. Some difference of two functions, equality of two functions, one-to-one function, on-to function, and bijective function also discussed here. In the uh, next remaining lecture, we will discuss about the inverse functions, finding inverse function, composite of inverse functions, composition of the functions, and composition of functions defined on finite sets, and plotting the functions in the graphs. Inverse functions we already discussed in the previous slide. Again I repeat it. If f inverse of y is equal to x, if and only if y is equal to f of x. This is the diagram of inverse function. You can say when the codomain becomes the domain x, the function f from x to y is a simple function, and y to x is the f inverse function. Here we give examples of f inverse. We given an arrow diagram for a function. We draw the arrow diagram for the inverse of this function. X f is here is the function from x to y. Arrow shows from where to where function goes. Mean to say x is the domain set and y is the codomain set. And if we discuss, if we said about the inverse function, then it's from y to x, so it's f inverse. So in f inverse, outputs becomes a b c d e and inputs becomes s t u v w, which was shown in this diagram. Finding an inverse. How can we find an inverse? I have already discussed in the previous slide also. If f of x is equal to 4x minus 1, from this you can find from this equation f of x is equal to y. Put the value of f of x 4x minus 1 equal to y. We find the value of x from this equation by basic algebra, y plus 1 divided by 4. So x is uh, f inverse of y. So this is the function, value function of f inverse of y, inverse function. So from this method we can find the inverse functions. Here is a theorem. If x and y are sets, here we prove that f inverse of y1 is equal to f inverse of y2. If it implies that y1 is equal to y2, it was already proved. We have to show that f inverse is 1 to 1, and then we show f inverse is on 2. For showing f inverse is 1 to 1, suppose y1 and y2 are the elements of y, such that f inverse of y1 is equal to f inverse of y2. So we must show that y1 is equal to y2. So there is let x is equal to f inverse y1, which is equal to f of inverse y2. Then for x belongs to x, by definition of f inverse, f of x is equal to y1. Since x is equal to f inverse of y1, f of x is equal to y2, since x is equal to f inverse y2. So consequently, y1 is equal to y2. Since each is equal to f of x, so this is what was to be shown. So this is what. Similarly, for f inverse on 2, we already proved this. You can see from the previous slide. Now, composition of functions. In the previous lecture, we also discussed about the composition, but here we discuss about the composition of functions by showing these diagrams. If f from x to y dash and g from y to z be function with the property that the range of y is a subset of the function of the domain of g, define a new function g of f, g composition f, you can say the g of f also from x to z, from x to z, as follows: g of f of x is equal to g of f of x for all x belongs to x, where g of f is read as g circle f and g of f of x is read as g of f of x. You can read it as g circle f or g composition f. So you can easily say that g of f of x. The function g of f is called the composition of f and g. Here x from, here is the function f from x to y. Here is the function g from y to z. Then g of f is the function from x to z. Let x is equal to 1, 2, 3, and y is a function a, b, c, d, and y prime is a, b, c, d, and y is the function which has the elements a, b, c, d, and e, and z is the function which has the elements x, y, and z. We define a function f from x to y prime and g from y to z. Then by the arrow diagrams we shown that x from x is equal to 1 to 3, x from f is from x to y, 1 to c, 2 with b, and 3 with a, and this is d. Now in g is defined as a to y, b to y, C to Z, D to Z, and E to Z. We draw the arrow diagram of g of x. Now, what's the range of g of f? The range of g of f is y and z, and the codomain of g of f is the whole z. Composition of functions defined on infinite sets. If we discuss about the sets, the g of f of 1 is equal to g of f of 1, which is equal to g of c, so it's z. If g of f of 2, it's equal to g of f of 2, so g of p is equal to some z. Composition which defined on finite sets, that x is equal to this, y is equal to y dash is equal to this, and y is equal to this, and x z is equal to this set. To find the arrow diagram for g of f, just trace the arrows all the way across x to z through y. The result is shown as below: 1 to z. So g of f of 1 is equal to g of f of 1, which is g of c. So z is equal to 1, g of c, and g of f of 2 is equal to g of f of 2, which is g of p, which is equal to y. So g of f of 3 is equal to g of f of 3. You can write here g circle f, you read it as g circle f 3. So this can be written g of f of 3, which is equal to g of a, which is equal to 1. So the range of g circle f is y z, which is the subset of z. So range is always the subset of codomain. Let f from z to z and g from z to z be two functions such that f of n is equal to n plus 1 for all n belongs to z, and g of n is equal to n square for all n belongs to the integers z. To find the composition g circle f and f circle g, and is these compositions are same, explain it. First we find the compositions g of f, g circle f of n, and it is equal to g of f of n. So g of f of n is equal to this. So here we put this value f of n. It may be read at m if we put it equal to m. So it's g of n. Now this whole value we put in this. So it will become n plus 1 square in this for all n belongs to z. F circle gn is equal to f of g of n. Now here we put the value of g of n from this. So n, which is equal to, and f of n square. Now we put in this the value of n. So the value of n is n square, so it's n square plus 1 for all n belongs to z. F from z to z, and this in the second part we explain that g circle f is equal to f circle g or not. Two functions from one set to another are equal if and only if they always take the same values. In this case, g circle f of 1 is equal to 1 plus 1 square, which is 4, whereas f circle g1 is equal to 1 square plus 1, which is 2. Thus the two functions are not equal, so this is not equal. Let x is equal to a, b, c, d, and y is equal to u, v, w, and suppose y f from x to y is given by the arrow diagram. We find f circle I x and pi y circle f, which is with the identity functions. We here find the composition with identity function. This is x, this is y. So ix identity function shows that which is the domain that will become a range. If A is input, A is output, B is input, B is output, C is input, C output, D input and D is output. So which is the domain that will become the range, and that also becomes in codomain. And if x is f is a function from x to y, so this will A to U, B to V, and C to V, D to U. So we find the values from this diagram here, which are defined. Note that in the previous slide, all elements x in x f of f circle ix is equal to f of x, so it is equal to simple f of x. By the definition of equality of functions, this means that f circle ix is equal to f. Similarly, the equality identity function of y circle f is equal to f can be verified by tracing through the arrow diagram. So a x to y and y to x, here is the identity function of y. It means u becomes u, v becomes v, w becomes w. Composition of function with its inverse. If let x is equal to abc and y is equal to xyz, define f from x to y by the following arrow diagram: x to y, a to z, b to x, c to y. Then f is 1 to 1 and 1 to. This f inverse exists and is found by tracing the arrow backwards. So f inverse means arrows from this to this. It means from f inverse y to x. So this will become the f inverse. Now composition here of f inverse. So these diagrams, which was shown in the previous slide also. So f inverse circle f, f inverse circle f of a is equal to f inverse of f of a. Here we put the value of f of a, which is z. So f inverse of z, which will become a. Similarly, in this case, f inverse of f b is equal to f inverse of f of b, which is equal to f inverse x, which is b. So f inverse of f c is equal to f inverse of f of c, which is f inverse of y, so it's c. And f inverse composition f, the composition of inverse with its function becomes the identity function. And similarly, we can show that f composition f inverse is equal to identity function with y. As the composition of one-to-one functions, we can read it easily. X to y, y to z. Here is the function f, and here is function g. A to w, and w goes to 1. X to f from x to y, and g from y to z. So the composition g, this will become x to z. From this x to z is also 1 to 1 functions. So these here is the tables of intervals, which is important. Finite interval AB, in the set description form, it may be written as the elements x. Xi is between A and B. It is open set. In open set, the boundary values are not included. In picture you can write it as in this form. And this is closed with the small brackets you can or parentheses. we can write the open interval, and for closed interval we have to write it within square brackets, and in this closed interval equality sign is also used, and it shows in the picture a and b, the values, the boundary values also involved in this interval. And if we half open, b is open, a closed, it means not equal to b, it's half open, so a included, b is not included. And if we write it in a b, a is open side and it's also half open, so here is not equality, here is only inequality, and here is equality. So b included, a is not included. We have to write the next value uh, which is greater than a. And for infinite, you can write if a infinity, it means that it's x which is x greater than a. So it's open interval, x greater than a to infinite, x is also not included. And this is closed. In infinite it is closed, it means x is included, and from x to onward all elements included, but the last is never is included. Minus infinity to b, you can write it b, it's b. We write the all values behind b, and if we write minus infinity to b, it means that minus infinity to b and closed interval, it means b included, and behind the b all values included. If we write this minus infinity to infinity, it both open and closed, so it's all the real numbers, it's a set of all real numbers. You can also write it as r. So here is the function y is equal to x square root. So the domain of this function we find is 0 to infinity, and y is equal to x to this, and the range of this function is 0 to infinity. It's very easy to find domain and range of the functions. So it's the Cartesian plane here shown. These are the positive x-axis and these are the negative x-axis. These are positive y-axis and this is negative y-axis. Here is the ordered pair P, point A, B. So if the point here shows that A has the value 2 point something and B has the value 3 point something. So here this point meets from this positive y-axis and from this positive x-axis. This is the origin. Here is the line if y is equal to x plus 1, a 3 4, b minus 2 minus 1. So from these 2 points we draw a line. 3 4 will fall here and minus 2 minus 1, it means both are negative, so this point is here and we meet these 2 points. This will draw a straight line. So this is also another diagram of y is equal to x square, graph of the function of the quadratic function. The quadratic function always have positive values. These are the values for domain and these are the values for range. So when we put 1, it will give 1 1, and if you put minus 1, then this will also gives the range or the output 1. So this will becomes the diagram, the graph of y is equal to x square is like a U shape or a hyperbola or a parabola. Here is the functions and the domain of these functions and range we have find here. You can try it at yourself also. Y is equal to x square. So its domain is all the real line, and its range is always positive, 0 to onward. This is the graph of y is equal to x mod, the absolute value. So this will also gives the straight lines, and at the upper half, positive half, it will become x if x is greater or equal to 0. It will become minus x if x is negative. So this is floor function graph. Is shown the values of floor function graph. You make it at your at the end. This is a lecture summary which we have discussed in this lecture. We discussed one-to-one function, onto function, bijective functions, and their graphs also. Thanks for this lecture, and next we will meet inshallah in the next lecture.